Hi everyone. Let's solve an optimization problem involving minimizing distance. We are given a function square root of x, and we must determine where the graph of square root of x is the closest to the point 5, 0. The graph is definitely not the closest here, because the distance is large. The graph is not the closest here, because again the distance is large. It appears that the point which is the closest to point 5, 0, that is on the graph of the function, is somewhere here. Let's give that point a label. Let's call it x, y. What we want to minimize here is the distance between the point x, y and 5, 0. What we are minimizing is distance. What is the formula for the distance between 2 points with given coordinates? The formula for the distance is square root of, and you first compute the difference in the x values of the 2 points, that is x minus 5, and you square that difference. Then you compute the difference in the y values. You get y minus 0. You square that difference, and then you add the results. This is the function we will try to minimize. Let's simplify it slightly, because y minus 0 is simply y, so I get square root of x minus 5 to the second power plus y squared. We were also given a constraint. We know that we cannot use any x and y we wish. We know that x and y must be, or the point x, y must be on the graph of the function square root of x, which means that the constraint here is that y equals square root of x. Let's use this constraint to rewrite our function in terms of only one variable. Wherever I used to have y, now I will have square root of x, and I get distance equals square root of x minus 5 squared plus, and instead of y, I will use square root of x squared. Let me simplify this expression. I get square root of, let's multiply out this parentheses. I get x squared minus 10x plus 25 plus x at the end. Square root gives me just x. Now negative 10x plus x gives me negative 9x. This is square root of x squared minus 9x plus 25. To find the x that minimizes the distance, I now have to take the derivative. To make my computations easier, I will find the minimum of a different function, the function distance squared, which is just x squared minus 9x plus 25. Note that the computations here will be much easier. And the reason why I'm allowed to do this is because the x that minimizes distance squared will also minimize distance. Think about it. Imagine I give you this green point, and I ask you, which point is closer to the green point? The orange point that I just added, or the pink point that I just added? Well, I believe that the point that is closer is the orange point. Now imagine I ask you a different question. Take the distance between the green point and the orange point, take the distance between the green point and the pink point, and square those distances. Which square will be smaller? I believe the square that is smaller is again this distance. If you take a small distance and you square it, you get a small number. If you take a big distance and you square it, you get a bigger number. Which means, in both cases, if you look at just distance or you look at distance squared, you always get that the orange point is the one that is closer to the green point. The same thing here. X that will minimize distance squared will also minimize the original distance. Let's name this function by a letter. I'll call it by g of x. I already used f of x. F of x was square root of x. Let's call this function by g of x. G of x is x squared minus 9x plus 25. To find critical numbers, I take the derivative, and I get 2x minus 9. Then I ask myself two questions. Is it possible for this derivative to not exist? And is it possible for this derivative to equal 0? It's not possible for this derivative to not exist because this is a linear function. To determine for what x's this derivative equals 0, I set 2x minus 9 equal to 0. This gives me that 2x is 9, which tells me that x is 9 divided by 2, which is the same thing as 4.5. Does this x give me the absolute maximum, the absolute minimum, or neither? Let's test it by taking the second derivative of the function g. When I take the second derivative, I get 2, which tells me that the function f is always concave up. And because this function is always concave up, we get not only a local minimum, but we get a global minimum. The function is always concave up, which means that x equal to 2, or x equal to 4.5, gives an absolute, or the absolute, minimum. Which means a point with x coordinate 4.5 is the closest to the point 5, 0. What is the y coordinate of that point? Whenever x is 4.5, the y coordinate is square root of x, which in our case is square root of 4.5. Which means that the point the closest to the point 5, 0 is the point with coordinates xy equal to 4.5 square root of 4.5.